Okay, having finished this example, let's move on to the next thing. I left a big blank here, don't know why. Oh well. Oops. There we are. So pause and copy that. So given a matrix A, and I guess you'd say it's a reduced version, not quite reduced echelon form, but oh well. We can use this to find bases for null A and call A. Okay, null A is something we've done before. We're basically just solving AX is equal to 0 and then writing out our solution in parametric vector form. So we take this reduced matrix, write out the corresponding equations here, and form our vector x in the usual way, pull things apart, and then your basis comes out here. It's these three vectors, without the parameters in front. I'm going to make a simplification here. These fractions are awkward, so what I can do is I can multiply, I can multiply this vector by 5 and multiply this vector by 5, and that will not do any harm. Okay, so what I did is I multiplied the last two vectors by 5 to get these two here. What you end up with is still a basis. We're just taking a scalar multiple of a basis element and still getting at the end a basis element. Okay, what about a basis for call A? Well, we're going to make use of a nice result here. Theorem 6, the pivot columns of A, in fact, form a basis for call A. So what do we mean here? So the pivot columns of A, these are my basis elements. So what I'm going to do here is I'm going to say, I have a pivot in the first column and the third column. Okay, but I'm going to be choosing my basis elements, not here. I'm going to choose them over here. So the first column and the third column, those, according to the theorem, are my basis elements. So pivot in the first column here, pivot in the third column. So therefore, I choose as my basis for call A, first column here, and the third column there. So scroll back down, let's see. So I write it out in more detail here. So pause and copy if you haven't done so already. So as I say, my basis is the first column of A, not the reduced version, but the original A. So I take the first column of A and the third column of A. And there's my basis there. Okay, notice that the word span is not there. Okay, if you put span there, that's not correct. A basis is a finite set. Okay, using this theorem 6, we can find a nice description of the range of a transformation. Okay, especially when we have a transformation in matrix form. Okay, so we saw earlier this fact here. The range of T is exactly the span of the columns of this matrix here, A here. So range of T is exactly call A. And theorem 6 allows me to find a basis for call A. So what do? I just take the A, reduce it until I can see where the pivots are. And here I see pivot columns just one. second column. So I take that column. And I have, I screwed up here. I have a typo here. Good thing I caught that. Should be a 3. So as we saw earlier, range of T is equal to col A. And col A can be nicely expressed as the span of a single vector. So pause and copy if you haven't done so already. And we'll move on. Okay, I want you to notice something. All right. Pause and copy first. Pause and copy. Okie dokie. We found a nice description of col A here. Originally, col A was the span of these 3 columns, and we were able to reduce it to the span of a single column. So that is some nice progress there. Okay, the span of 3 columns was reduced to the span of a single column. So we've simplified our col A in a sense. And how about up above? In the preceding example, here we found that col A is the span of these 2 guys. So col A is the span of 2 vectors. Whereas at the beginning of the question, col A is the span of these 5 columns. Okay, so we went from 5 columns to 2 columns. So progress. So let's introduce a theorem that kind of formalizes this. So we call this the spanning set theorem. So pause and copy. Okay, we start with a subspace, which is a span of some vectors, and we want to kind of whittle this down. We want to simplify this as much as possible. We want to remove any extra elements here. So what the theorem says is that if one of these vectors is a linear combination of the others, then you can delete it. You can just totally cross it out, and this equal sign will still be true. Okay, so you don't lose anything. You have kind of simplified your description of H. Part 2 says you can just keep on doing this, and eventually you will arrive at something perfect, a basis. Okay, you just keep on whittling this down, keep on reducing it, and eventually you'll run out of vectors to remove. And when you get there, you can be sure that you have a basis.